right, so now we're going to look at type 2 boundary conditions. And, this is where at first you may think, well, what's different? And they're saying, okay, we're going to put the end of the rod into a bath of some kind, where the bath, maybe it's a very big bath, and but that it somehow we essentially decide its temperature doesn't change, and so this has well, I'm sorry, its temperature doesn't change. Its temperature could fluctuate in this bath. However, it is not specifically keeping the end here of the rod at a particular temperature. So in other words, heat could either enter the rod from the bath, or heat could leave the rod from the bath. And again, we're assuming insulation. There's my furry insulation. And so, they're using the notation that at this end, the temperature is G1 of T, and this end, the temperature is G2 of T. But again, you're not holding the end of the rod at a particular temperature. It's the surrounding medium that the rod is immersed in. And so heat could go, I'll draw it over here, could go either way. Okay, if the rod's hotter than the bath, the heat should leave. If the rod is colder than the bath, it should enter the heat should enter the rod. Now they get into all this stuff about flux and so forth. Now flux, all the flux is flux of heat is simply the rate of change of the heat at a point in a direction normal to. Now, in as long as we're in real physical space and all that, then we could say perpendicular to the surface where the heat changes. Okay, so, all that means is in one dimension, if we think of this very, very thin rod in one dimension, then, I have that rod surface like this. And so the flux is perpendicular to this thing. It's either going this way or that way, but you see it's perpendicular, same here. It's either going this way or that way. But, let's go back to like that circular disc. Suppose you put a circular disc from the earlier boundary conditions, and you had a wavy, I'll make it wavy here with bath, on the edges, but it's insulated on the top and bottom, so only the edges can go on. Well, in this case, it's just saying, well, the flux at any given point would be in, this direction, one of these two, in or out. Same thing here, in or out. Okay, but perpendicular to the surface right at that point. Okay, so that's all it's talking about there. When you get into 2 dimensions, you have to start talking about things like gradients and stuff like that with your partial derivatives. But in one dimension, right, we'll have, of course, a partial derivative because we've got both t and x. But if we just forget about t for a moment, then our flux is just dx dt. Okay, so that's oh, sorry, no, I did that wrong. I picked it. I was thinking, sorry, at least I fixed that real quick, or we'll fix it real quick. Sorry about that. Dx dt, no. The flux, remember, is the rate of change of the heat at a point. Now, I didn't say the rate of change of heat with respect to what, but that would be du dx. So I started thinking of x as the independent variable. Sorry about that. But flux is just du dx. Okay, so it's the rate of change of the heat with respect to the space here. Okay, so it's just du dx, and that's all it is. Okay. Now, and we won't worry about this stuff down here. Okay, so that's one thing about the flux. And then now they use a slightly different notation here than I would have used, I think, in that they put their constant. Let's see. Yeah, they put a constant on their derivative here, du dx. I probably wouldn't start it that way, but that's fine. So they're saying, one way to talk about flux is k times du dx, and we'll change this to partials here in a moment and all that. But then it's also the case that we know from Newton's law of cooling, and you should have seen this in either Calculus 1 or Calculus 2. If you had me, you definitely saw it in Calculus 1. I think if you had Lagrange, you probably saw it in Calculus 1, but I'm not sure. And I have no idea if you had Calculus 1 from Ratliff, if you happen to see Newton's law of cooling. But it simply says that rate of change there is simply proportional. So in that case, they would say the flux is proportional. And in this text, they are using an H, I guess. An H times the difference in the heats. So at the left end, where u is 0, you would have u of 0. Not u is 0, the x is 0. You would have u of 0 minus your g1. Now, I didn't make it as a function of t yet because we'll add that in. But you would have that at, this is at x equals 0. And then at the other end, you've got flux is equal to h actually they do a minus h of u of L minus G2. So this is x equal L. All right, so now what they've done in order to make this happen, okay, so if u of 0 is greater than G1, right, then this flux is greater than 0. Okay, so the let's see, so I got to look at something here and what they have written down. Sorry about that. Give me a moment. I see. Okay. Then, yeah, I'd forgotten that they put the actually the minus back here. Okay, so they would have a minus, and they actually have a KA or something like that, but they put a minus on that K. So K is greater than 0, but so they put a minus there. Okay, so if this is the case, then this this flux here would be greater than 0. And on the other hand, if you know, u of L is greater than G2, then it would have the flux as less than 0. Okay, because of that negative there. And I think I see. Okay, so yeah, I have to be really careful here because they did the minus sign sort of backward of what I would do. So again, let's change that and change that. Yeah, so they didn't really start looking at this until after they did their signs, I see. So so let's, yeah, just erase that from memory, you know, kind of like last lecture or something. Yeah, so they're saying that they have something like this. So we won't worry about that part for the moment. And so we'll put, though, the two flux definitions together. And so we have, according to them, then with these boundary conditions, that, and again, I haven't added t yet, so I'm just going to write u of u sub x. Okay, so the derivative of u with respect to x is equal to, so if that's a minus and the k is a minus, then we'll get an h over k, which is a positive, and u of 0 minus g1. And then down here, we'll have a minus because this h was a plus, but the k was a minus. So u of L minus G2. Okay, so that's what they get. And then notice in this case, okay, if u is greater, right? So again, I'll write that down now. If u of 0 is greater than G1, then, you know, as you, and I'll put here, what do they say? If u of L is greater than G2. So the picture of that, they draw this, you know, something like, and I'll just do something like this. So we'll say, you know, here's 0, here's L. They just use a point x0. But we'll say, you know, this is hot, this is cold, and cold. Okay, when u sub x, u sub x is greater than 0, and here u sub x is less than 0, then actually though, notice what the heat flow is doing. It, you know, here the heat flow is going that way, and here the heat flow is going to the right. Okay, so this is how they are imagining what happens here. Okay, let me look at how they finish it up here. I haven't seen that, and so I'm going to pause it for a second and come back. All right, so, you know, I think this sort of thing here just seems kind of counterintuitive, right? Because, you know, when we think of a positive derivative, we tend to think of, you know, a direction going up and goes to the right. But you see, that's exactly what is happening. So the heat flow is going this way. Okay, this is the flow. However, the derivative itself, notice u, the heat itself, or sorry, yeah, the function itself is going from a colder temperature, like here, up to a hotter temperature there, right? Shouldn't u sub x be greater than 0? Okay, and so, you know, what looks, I think, intuitively kind of backward, it is correct. Okay, so u sub x is greater than 0. That means, you know, u is higher here than here, and so its derivative should be positive. And the same thing here, you know, the heat was higher, now it's lower. The derivative should be negative, but the flow is in that opposite direction of the derivative. Okay, and that they're calling this Fourier's law. French, Fourier. Okay, so then they finally just finish it up with, typically they let h over k equal a lambda. And so our boundary conditions are that, and I'll add the t in now. So the partial with respect to x at time zero, at x0 and time t is equal to a lambda now. We have that there. U at 0 and t minus, and now g1 could be a function of t. And similarly, u sub x at L and t is minus lambda u of L and t minus g2 of t. Now, and with the boundary conditions in some sort of bath, again, certainly over time, you would expect that if the baths are constant, right? So you've got a constant temperature here, maybe of G1, constant temperature in this bath of G2, then over time, you would expect, we'll make everything positive here, so we'll say there's G2, up here's G1, put L here, then yeah, in the long run, we should see our straight line like that. But in this case, you know, say we start with an initial condition of, you know, something like this. Here's u of x and 0. Then we wouldn't immediately actually expect this to drop here like we had done before, right? In the others, when we went to some T1, we initially tied this end here down to this point here, and this end here up to that point there. But now it might be a much slower sort of thing. So at T1, or T equals 1, you know, we might expect to see, you know, something like this. So here would be u of x and 1. And again, if G1 and G2 are functions of t, well, then all bets are off. I have no idea what it's going to do. I'd have to get a solution to the partial differential equation to see. Okay. But that's the idea of these boundary conditions. You know, we would expect in the long run, if they're constant, but a bath, it would make it to that straight line eventually, but in a slightly different way than if the ends were held at a constant temperature. And then if they depend on T, who knows? All bets are off there. Okay, so that is type 2.